Hey everybody, my name is Anthony Sanchez, and I'm a postdoctoral scholar at the University of California at San Diego. I'll be your mentor this semester for the Homogeneous Dynamics branch of the Big Ideas in Dynamics Initiative. In this lecture, I'll introduce us to some characters that show up in many homogeneous dynamic stories, namely the space of lattices and the Siegel formula. Another reason why I want to talk about this is because a variant of this idea is one of the key ideas that show up in the Eskin-McMullen article that we'll read together this semester. And with that, let's go ahead and get started. So I'll share my screen. And I'll introduce us to the first, to kind of one of the big characters of today's talk. Let SLNR denote the set of n by n matrices with real entries such that the determinant of G is equal to 1. And now that we have SLNR, I want to give this the notion of a lattice. So a unimodular lattice lambda in Rn is a set of the form lambda is equal to G of Zn, where G is inside of SLNR. Okay, and so the word unimodular here is corresponding to the fact that we're looking at matrices that have determinant 1. I'm kind of normalizing these lattices. And then a lattice, then another way of thinking about this is just some discrete subgroup of Rn of maximal rank. And so as an example, let's look at n is equal to 2. Actually, in a lot of the lectures that we'll do, I think it's really instructive to think about what everything looks like in the n is equal to 2 case. It really does have a lot of the kind of important ideas that we'll need. So let's consider this set lambda given by integer linear combinations of the following two vectors, 1, 0, and 1, 1. Then this set right here is a lattice in R2. All right, and geometrically, what is this set right here? So this is nothing other than, well, I'll grab this first vector right here, 1, 0, 1, 0, and then I'll grab this second vector over here, that is 1, 1. And I'll start looking at integer linear combinations of them. So if I grab these two vectors and I add them, I'll get the vector 2, 1. If I have the first basis vector and I add it to itself, I'll get the vector 2, 0, and so on. If I subtract the first basis vector from itself, I'll get 0. From this, I can kind of keep playing this game. And you see that geometrically that this lattice inside of R2 is just this discrete grid in the plane. All right, but it doesn't exactly align with the definition that we gave above. But I can see that this is a lattice with that definition by considering, or let's say notice, that lambda can equivalently be written as 1, 1, 0, 1 times Z2. But if I look at this picture here on the left, this is exactly the integer points of the plane, right? And so I'm able to realize that additionally, lambda can be written as, let's say, the identity matrix times Z2. So that different choices of G may yield the exact same lattice. So there's some redundancy in this definition. So now let's let X sub n denote the space of all of these unimodular lattices, the space of space. So as a set, X sub n is just sets of the form GZN, where G is inside of SL2R. And this is a perfectly good description of this set. I want to point out, though, that we saw above, there's some redundancy in this definition, right? Different G's may yield the exact same lattice. So how do we take care of this kind of redundancy? I want to recall for us the orbit stabilizer theorem from like a first course in group theory. So notice that SLNR naturally acts on the space of lattices by the linear action. Which is to say that if I have one of these grids, what I'll do to all these points inside of these grids is multiply it by the same matrix G, and that'll give me a new grid, right? So I guess, yeah. And so now I want to utilize the orbit stabilizer theorem that says that anytime I have a group acting on a set, I'm able to identify what this set is. So the orbit stabilizer theorem says that I can identify this space. So if I grab a point in the space, let's take, for example, Zn, and then I push it by all of SLNR, that this is in bijective correspondence with SLNR, the group, mod the stabilizer of the point that I'm choosing, in this case Zn, inside of SLNR, namely the set of points that preserve Zn. And the map here is just I grab a lattice and then I take it to this coset given by the stabilizer. All right, and why do I say that this is helping us identify what this nice geometric space is? Well, notice that if I grab Zn and I push it around by all of SLNR, I'm exactly recovering the space of lattices, namely everything inside of Ln. And now, on the other hand, what is the stabilizer? It's not a very difficult exercise to see that if I want to keep kind of these grid points at integer points, then I better only multiply by elements inside of SLNZ. And in fact, all of SLNZ is going to preserve this integer lattice, which is to say that the stabilizer is SLNZ. And this is what I mean by we can identify the space. So the space of lattices, which is this geometric space consisting of lattices in Rn, is nothing other than this coset space, SLNR mod SLNZ. And I keep saying this coset space. It's not a group because SLNZ is not is a subgroup of SLNR, but it's not a normal subgroup of SLNR. So this is indeed just a coset space. It's not actually a group. All right, and now I want to give some extra structure to this space of lattices. And in order to do that, I'll recall another very important notion that kind of shows up everywhere in homogeneous dynamics. So recall that there is a unique regular SLNR invariant measure on SLNR that I'll briefly, that called, I won't denote it by anything, called the Haar measure. Right, and so similar to the orbit stabilizer theorem, if you need a refresher on this, open up any book on functional analysis. So for SLNR, there is this regular measure where regular means that I can approximate measurable sets from below by compact sets and from above by open sets. That's SLNR invariant, which means that if I have a measurable set and I translate it by a group element inside of SLNR, and in this case on either side, that is going to have the exact same measure as just the set that I started off with. And using the fact that SLNR itself has something called the Haar measure, one is able to show using the Haar measure and some hyperbolic geometry. That I won't do in today's lecture, but I encourage you to ask me about it during the office hours. That there is a measure on Xn with these properties. And so by abuse of kind of notation, even though Xn is not a group, it's just a coset space, we call this measure the Haar measure. And so when I say these properties, it reminded me that there's a small caveat in what I've written here. This word unique is only up to scaling, right? If you handed me a measure that satisfied all of these properties, I could multiply it by 3, and my measure is going to continue to have all of these properties. So this uniqueness is only uniqueness up to scaling. And that'll essentially be true of all of the statements that I say today. But once you kind of fix a normalization for the measure, then I'm able to kind of talk about uniqueness in an honest way. All right, and so now to simplify the notation a little bit, I'm going to let G denote SLNR and gamma denote SLNZ and denote the Haar measure on a space of lattices, which with the simplified notation is just G mod gamma, by M sub G mod gamma. And we're actually almost there in terms of the kind of concepts I'll need to introduce us to the Siegel formula. There's one more bit of notation or one more concept that I'll have to introduce us to before I can talk to you about the Siegel formula. So let Zn prim denote the set of vectors inside of Zn such that if I write down this vector as in components, the GCD of the components are all equal to 1. Okay, and so this is kind of the easiest way of kind of writing down the primitive lattice points. But what do these things correspond to geometrically? Again, let's look at the n is equal to 2 case. And let's look at, the integer lattice. Then if I grab this vector here, E1, the GCD is going to be between 0 and 1 is going to be 1. But if I was to grab another vector, let's say this one right here, 2, 2, the GCD of this is going to be, if I drew this a little bit better, the GCD of this is not going to be 1, it's going to be 2. So what does this mean geometrically, this kind of GCD condition? The way you should kind of imagine this is pretend you're standing at the origin. And now pretend at all of the integer points, we place on top of it an infinitely high tree. Then the primitive lattice points are exactly the ones that you can see from the origin, right? So if I'm standing at the origin, I'm able to see this vector E1. I'm able to see there just by looking, in that direction. On the other hand, if I look in the direction of 2, 2, I'm not able to see that vector. Why? Because it's being blocked from view by the vector 1, 1, which is inside of Z2 prim. So while this kind of setup is the easiest way of writing down what the primitive lattice points are, geometrically, you should just think about these points as a set of visible lattice points from the origin. And with that, I can introduce to us the Siegel transform. The Siegel transform is going to be a transformation on function spaces. So what kind of functions am I interested in? I'm interested in continuous functions with compact support in Rn, and I want to map this to continuous functions with compact support on my coset space, G mod gamma, on the space of lattices. And how do I want to define this transformation? I want to define this by, if I grab one of these functions, well, it needs to live on the space of lattices. So let me go ahead and eat a coset or a lattice. It's the same thing. And how do I want to do this? I want to just sum over all of the. So let's say it this way. I want to. This function is as a function on Rn. So I want to eat vectors. Which vectors do I want to eat? I want to eat the vectors that are lying inside of the primitive lattice points of this lattice, which are just G of the primitive lattice points of the standard integer lattice. And a short calculation can confirm for us that another way of writing this sum is as V inside of primitive lattice points of their shifts. Okay, and so a couple of things probably will kind of raise some eyebrows with this definition. First of all, the primitive lattice points are infinite. So this looks like an infinite sum. But that's exactly why I looked at continuous functions with compact support. By virtue of this having compact support, I'm looking at this discrete set. And inside of this compact set, I'm only going to have finitely many points. So this is always going to be a finite sum. So there's a well-defined sum. Additionally, you may worry about whether this is well-defined, right? So if I was to take, like this lattice is only defined up to SL and Z. So if I take a different coset representative, does this change the sum? And I'll leave that as a small exercise to say that changing the coset representative is just gonna kind of shuffle the sum, but the sum will remain the same. And armed with that, I can state for us the Siegel formula. So for a function on Rn, this continuous and compact support, I may be interested in integrating the Siegel transform of this function with respect to this Haar measure that lives on G mod gamma on the space of lattices. And how can I integrate this function? Well, I'm able to integrate this very simply. I just have to integrate the original function over Rn with respect to Lebesgue measure on Rn, at least up to a constant. So now a couple of comments that I want to make about this is, what is this constant here? This constant ends up actually being the Riemann zeta function evaluated at n. So if n is equal to 2, this is going to be pi squared over 6. But for our purposes, I'm not interested in this constant at all. I'm more interested in the fact that this formula allows me to integrate certain functions on the space of lattices. How do I integrate them? I just integrate some function on Rn, something that I've been doing my whole life. Another comment that I want to make about this is if I select appropriate functions, for example, let me choose f to be the indicator function on the ball of radius r, then this is going to tell me how many primitive lattice points I should expect to see on average in a ball of radius r. And so we should be careful there. I should take a smooth approximation of this indicator set. But yeah, that's a digression. All right. And so now, before I kind of leave us today, I want to set the stage a little bit for the proof and introduce for us a number of kind of natural things that show up in this proof. Okay. And so to do that, and then in the next lecture, I'll put all of these pieces together and I'll prove the Siegel formula for us. Namely, that I can integrate certain functions on the space of lattices by just integrating them on Rn. So to do that, let me let EI denote the standard basis vectors on Rn. So for example, E1 is the vector that has 1 in the first component and 0 everywhere else. All right. And now I want to recall for us that one of the things that I want to do with today's lecture is just really let us know orbit stabilizer theorem is awesome because it lets us identify stuff. So I want to recall for us the very obvious linear action of G on Rn. By looking at the linear action, we have the following, thanks to the orbit stabilizer theorem. So let me just go ahead and grab some vector inside of Rn, maybe E1, and let me look at its G orbit, right? Let me look at, remember G is SLNR. So let me look at the orbit of E1 under SLNR. Then the orbit stabilizer theorem tells us that I can think about this just as G mod the stabilizer of E1 inside of G. All right, so what is this set? Well, on the left-hand side, if I grab some small g and I multiply it against the first basis vector, it's just going to record for me the first column. So now we have to ask ourselves, what are the possible first columns of an invertible matrix, of a determinant 1 matrix? Well, the possible first columns are going to be anything that I want. Well, it's not invertible. Sorry, I meant to say it is invertible. So it's anything that I want except for 0. Because if I allowed 0 in there, then I wouldn't be invertible anymore. All right. And now let's think about this stabilizer a little bit. And the stabilizer is literally asking me, what matrices G do I have G of E1 is equal to E1? Well, this is only going to restrict what I look like in the first coordinate. In the first coordinate, I have to be E1. And then I can be anything else outside of there, right? This is E1. And then I can be anything else that I want outside of there, all right? So in this case, I can be n-1 points, any n-1 points. So this is going to be some vector inside of Rn minus 1. And now what could be down here? Well, similarly, this could be anything that I want it to be, so long as I recall that G itself has determinant 1. So whatever I put in here, I have to make sure it gives me determinant 1. And so this restricts what G prime can be a little bit. G prime has to have determinant equal to 1. That is to say that G tilde has to be inside of SLN minus 1 of R. All right. And so let me denote be the stable. Let me denote the stabilizer by G prime. Now I can think about this now as nothing more than G mod G prime, right? So this kind of quotient right here, G mod G prime, right now it looks relatively unmotivated, right? And it's very nice that we have this form for it. I'll talk about this very shortly, but this form for it means that G prime is nothing other than the group SLN minus 1 of R, semi-direct Rn minus 1. I'll write this in a moment, don't worry. But this quotient right here, right now unmotivated, is nothing more than a fancy way of rewriting Rn, at least off 0. Okay, so now let me go ahead and do as I promised and write this. Hence, G prime, I can think about this geometrically as SLN minus 1 of R, semi-direct Rn minus 1. And I'll leave it as an exercise for you all to kind of recall this semi-direct product operation and to realize that the operation that goes on in there is actually exactly what's happening with this matrix multiplication, right? So this is going to be, as a group, this is going to be the set of pairs G tilde V, or how would I call it there? I call it X. Gx, such that G tilde is inside of SLN minus 1 of R, and then X is inside of Rn minus 1. And it comes equipped with an operation that when I multiply two ordered pairs of this form, I'm going to multiply them in the way indicated by this kind of matrix multiplication. All right, and now a similar computation for SLNZ gamma shows the following. If I was to grab gamma and look at the orbit of, say, E1, then the orbit stabilizer theorem tells me that this is the same thing as gamma mod the stabilizer gamma of E1. So what is this geometrically? If I grab something inside of SLNZ and then I look at all possible first columns of it, what should I obtain? I think a really good guess is that you'll end up with just the integer lattice points. But in fact, closer inspection will tell us that we're only going to get the primitive lattice points. And you should think about this for n is equal to 2, right? We can never, I encourage you to like plug in n is equal to 2 and show that we can't get the vector 2, 2, for example. This is like a consequence of Euclidean like algorithm, basically. But the thing that I kind of want to point out here is that this kind of the primitive integer lattice points and actually Rn are things that show up in the Siegel transform. And I'm able to use the orbit stabilizer theorem to write them down as a coset space. And I hope to utilize the coset space very shortly. but I guess I'm getting ahead of myself. We haven't figured out what the stabilizer is. So in exactly the same way that we showed what the stabilizer of this matrix was with respect for G, I'm able to show that this stabilizer is nothing more than G prime, the stabilizer in G, intersect integer matrices. And then I'll denote this as gamma prime. So I can identify this space as gamma mod gamma prime. So the gamma mod gamma prime is just this discrete space. Geometrically, it's just another way of writing down the primitive integer points. Okay? And now let me point out one more thing related to these spaces. Note that G prime mod gamma prime geometrically is the space of affine lattices in Rn minus 1. Right? So what do I mean by an affine lattice? It's just like a lattice, right? So I'll grab some element inside of SLN minus 1. And then I'll push Zn minus 1 by that. So where does the word affine come from? It comes from the fact that I'm allowing these grids to be shifted off the origin. Plus x, where G tilde is inside of SLN minus 1 of R. And this vector is inside of Rn minus 1. Okay, so these spaces that I'm kind of introducing here come with their own kind of rich geometric structure. All right, and now I've introduced for us some spaces that tangentially are related to the Siegel transform, right? The Siegel transform is taking in functions on Rn. The Siegel transform is summing over the primitive integer points. And it's cool that I can write these down as these coset spaces, but how are they all related together? All right, and so I want to draw as kind of the last thing that I'll do for today is I want to draw a diagram that I really encourage you to like think about. I don't think it'll be an obvious diagram. It wouldn't be the first diagram you would look at maybe, but it relates all of these spaces together. These spaces, thanks to the orbit stabilizer theorem, are all related by the following. If I now look at G mod gamma prime, remember, maybe I'll write that here. Gamma prime is just the stabilizer with respect to G intersect gamma. So if I grab this space right here, then I can push down to G mod gamma with some map that I'll call pi 1. How do I do this? All right, if I grab some element inside of this coset space, how do I get a coset in here? I'm just going to drop the gamma prime. Right, so gamma prime is smaller than gamma. It's an intersection with something else. And so now when I take G and mod it out by this smaller thing, I should think about this as like a cover of the thing that I would get G mod gamma, right? Gamma is bigger, so G mod gamma is going to be smaller. And so in that way, it's kind of like a cover, all right? Additionally, I have another projection map, pi 2, that takes G mod gamma prime into G mod G prime in exactly the same way. I'll take a coset into this coset. All right, and these are exactly the spaces that are appearing in the Siegel transform, right? G mod gamma is the space of lattices. That's where we're integrating everything. And then G mod G prime, recall by the orbit stabilizer, is just a very fancy way of writing down Rn, at least off of 0. All right, and now let me introduce some more structure into here and some more spaces that will become very important for us. What are the fibers of this map? All right, and what I mean by this is when do I have two different points upstairs that say under pi 1 will map to the same thing? All right, and let's look at what this fiber is for just the identity coset, let's say. All right, so the identity coset is exactly, let me give myself a little bit more space. The identity coset is exactly the set of points inside the set of points upstairs. This is what I said, right? That map to the identity coset downstairs. So expanding this a little bit, I know what pi 1 of this element is. This is just G gamma. Oh, and I wanted the identity coset. So this is going to give me the equation G gamma is equal to gamma, which means that I am the identity coset. So that G is only defined up to gamma. All right. So the set of points upstairs that map to the same thing under pi 1 are exactly given by gamma. So I should think about this as the fiber is just gamma in the coset space. So gamma mod gamma prime. And then I want to point out that earlier the orbit stabilizer theorem told us that this coset right here is nothing more than the primitive integer points. All right, and a similar computation that I'll leave for you will show that the fiber of pi 2 is going to be G prime mod gamma prime, which is, I think I wrote it up here, just the space of affine lattices. All right, and so that'll conclude for us the first lecture. What did I do? I introduced to us kind of the space of lattices and the Siegel transform, and I said that Siegel's formula tells us that we're able to compute certain functions in the space of lattices really quickly. And then what did I do right after that? I introduced us to a slew of different spaces, and I didn't motivate these spaces exactly. They seem, at least at first glance, like they could be related, right? All of these spaces, first of all, are very nice geometric spaces. And a lot of these spaces come up very naturally in Siegel's formula, right? On the bottom left here, we have the space of lattices. On the bottom right here, we have Rn. The fiber of pi 1 is given by the primitive integer points, which show up in Siegel's transform. So right now, this is a very unmotivated diagram, but in this next lecture, all of this buildup, all of this orbit stabilizer theorem is going to come in, use this diagram, and very quickly-ish prove Siegel's formula. All right, so I look forward to doing that in the next lecture, and I'll talk to you soon.